Hey, how's it going everyone? Welcome to this video. Today we're looking at coordinate geometry applications of differentiation. So in the last chapter we've had a look at derivatives. A derivative measures the gradient of the tangent to a curve at any point. Because we're looking at tangents, a tangent is basically a straight line, and we can work out what the equation of that straight line is. And that's what we're going to have a look at today. So a straight line equation, if we remember back to linear equations, we can work that out by if we have the point, if we know what the point x1, y1 is, okay, it goes through that straight line, we can work out the equation of that straight line by this formula. If we've got this curve y equals f of x, and we want to work out what that tangent is at a particular point P, we can work out what the gradient of that tangent is at the point by finding the derivative of f of x and using p to find the gradient. So m was going to be that derivative at point P. So using these two bits of information, we're going to have a look at example 5. So we've got y equals 2x cubed plus x squared, and we're finding the equation of the tangent at x equals minus 2. So the first thing we need to work out is our point P. So what is our point P? Well, we already know that x is minus 2, and we need to work out what our y value is. And we do that by just summing in the point x equals minus 2 into our original equation. So minus 2 cubed is going to be minus 8, times 2 is minus 16, and we've got minus 2 squared, so it's just plus 4. Work that out, we get minus 12. So our y coordinate in this case is minus 12. So the next thing we need to work out is what our derivative is for the original equation. So dy dx, we've got 2x cubed plus x squared. Using our methods of finding derivatives, bring the power down and multiply it. We've got x and take 1 to the original power. So 3 take 1 is 2 plus, okay, same thing, bring the power down, we get 2 and x. Tidy it up, we get 6x squared plus 2x. Now we need to work out what the gradient at that tangent is, and we use that by putting in our minus 2. So at our gradient m is going to be 6 times minus 2 squared plus 2 times minus 2. And tidy that up. We get 20. So we can say the gradient of the tangent is 20. And using our formula to find equations of straight lines, we have y take y1 equals the gradient x take x1. So using our bits of information, we have y take, and y1 is going to be minus 12. Good thing to use brackets. M we just worked out was 20. X take x1, which was minus 2. Again, use brackets. So two negatives make a positive. And same thing over there. Next thing, we can expand the brackets. And then take 12. Oh, Sorry, that should be 40. And 40 take 12 in there. So our final answer is going to be 20x plus 28. So that's our equation of the tangent. The next thing we're going to look at is coordinate geometry. So worked example 6, we've got the point 2, 1, and the curve y equals a quarter x squared, and a line is drawn perpendicular to the tangent to the curve at that point. This line meets the curve again at point Q. So I'll just draw out what it looks like. So we've got a set of axes. Our equation, a quarter x squared, looks something like this. And then we have a tangent at the point 2, 1. So cross 2, up 1. So somewhere over here, we've got a tangent. We'll call that point P. And then this line, so a line is perpendicular to the tangent. So perpendicular meaning at right angles. So we find the tangent and there's a perpendicular line, and that line will meet again over here at point Q. And so what we want to work out is where that point is at Q. So to start things off, we've got our equation. Need to find the equation of the tangent, or at least the gradient. So we've got y equals a quarter x squared. Need to find the gradient, so find the derivative. Bring 2 down, we get a half x. And at the point 2, 1, we have our dy dx is going to be a half times 2, and a half times 2 is 1. So our gradient of the tangent is 1. If we remember perpendicular lines, means that the gradient of one line times the other line is equal to -1. And so what we have is, if the gradient m1, which is our tangent, so using that, we've got 1 times the gradient of the other line, which is q, is going to be -1. So therefore, we can say the gradient of our second line is actually -1. Again, using our equation, y take y1 equals m x take x1. We know that m is going to be -1. We've got the point 2, 1. So let's put those in. So we've got y take y1, which is 1. M, which is -1. X take x1, which is 2. So simplifying that, you get y equals -x plus 3. So the point Q lines on the line y equals -x plus 3, and the curve y equals a quarter x squared at Q. So we've got two lines meeting each other. So we've just worked out the equation of that line there. We know that line here. So when we're finding the point where they intersect, essentially we're doing simultaneous equations. So we can say that a quarter x squared, which was our original curve, is going to be the same point where this equation occurs or goes to. So we get make them equal to each other. Simplifying a bit, we get x squared equals minus 4x plus 12. Therefore, we can say x squared plus 4x take 12 equals 0. Factorize our quadratic, because that's what we've got now. We'll get x plus 6, x take 2 equals 0. So either x equals minus 6 or x equals positive 2. Now, we've already worked out that positive 2 is that point there, which is not the one we want, so we actually want this one here. So if we sub that back into either equation, this one's going to be easier. We'll call that equation 2. We'll say y coordinate is going to be minus 6 plus 3, which is going to be 9. So the point Q has coordinates minus 6, positive 9. Now, the second part of the question says to calculate the magnitude of the angle that the line passing through Q and the point 2,1 makes with the positive direction of the x-axis. So for the angle of inclination, M, make a new page, M is going to be tan theta, as the gradient of the line passing through Q and the point 2,1 is minus 1, which is what we worked out before. We can say that tan theta is equal to minus 1. Since the gradient is negative, the required angle is going to be obtuse. So the second quadrant solution is going to be theta equals 180 take the inverse of minus 1. We get 180 take 45. So we get 135. So we can say the angle made with the positive direction of the x-axis is 135 degrees. The last little bit we're going to have a look at is increasing and decreasing functions. So if we have a curve, any curve, and we look at it from the negatives to the positives, we can have a look at the tangent at each point along the curve. So if you imagine each point along here and think of what the gradient or the tangent is. So this one here, we've got a positive gradient. It's a positive straight line. It's going up, as with that one and that one. It means that the gradient, the curve is increasing. So if the derivative of the curve is greater than 0, so the tangent is greater than 0, it's positive, it means that the function is increasing as x increases. And if it's negative, so these points here, if we drew tangents, it means that the curve is decreasing. So we say if f of x is less than 0, the function is decreasing as x increases. So example 7, over what domain interval is the function f of x equal 1/3 x cubed plus 7 over 2x squared plus 6x take 5 decreasing. And to do that, we first need to find the derivative. So the derivative of f of x, bring the power down, take 1 from the power. And we're looking for when the derivative is decreasing. So from the last slide we said decreasing is when the derivative is less than 0. So we say our function or our derivative, when is that less than 0? So we're solving for what points it's less than 0. We can factorize this. And so our zeros are either -6 or -1. Using our sign diagrams, we've got -6 and -1. We've got a positive equation or positive quadratic, so it's going to be looking like that. And so we can say the function is decreasing. It's less than 0 for all these values in here. So decreasing between the interval of -6 and -1, and should be just less than, sorry. So it's decreasing between -6 and -1. Part B, form the equation of the tangent to the curve x squared plus ax plus 4 at the point where x equals -1. So we've got this new equation here. Need to figure out our y value when x is going to be -1. So we have y equals and simplifying that, we get 5 take a. So we have the point at -1, 5 take a. Our gradient if we work out the gradient, we get 2x plus a. And if we use the point, we'll say t. So if we use our point t, we can say 5 take a is equal to 2 times -1 plus a. sorry, our gradient. So we're looking at gradient. So using our gradient, we use the point at -1. We get -2 plus a, so that's our gradient. Need to form the equation of the tangent. So again, we're going to use our formula. Point y is going to be 5 take a. M we just worked out as -2 plus a. X take x1, which was -1. Expand the brackets. And we can add 5 take a. Expand these. A's cancel. We get -2 and 5 is +3. So we get -2x plus xa plus 3. And we can factorize that as -2 plus a times x plus 3. So here's our equation of the straight line. We've got something x plus c, and that's all we can do. So that's part B. Part I. And the next part says to hence find the values of a for which the function is increasing at x equals -1. So increasing at -1. So if a function is increasing, the tangent to its curve must have a positive gradient. So the gradient of the tangent at x equals 1 was -2 plus a. So we say the function is increasing at -1 when -2 plus a is greater than 0. So we can say when a is greater than 2. So that's part BII. Okay, so that's it for a moment at 13.4. The next video I'm going to look at Newton's method. I need to do that as a separate video. So I'll leave it here. Thanks for watching.